As you can see, we have moved from the botanical garden to our lab. And what you have seen in the tropical garden house were tendrils. Those are tiny structures of plants which are able to curl. Now I want to show to Nick and to you that those tendrils can also be made from synthetic materials. And this is a small experiment that we have prepared here to demonstrate. And we want to show that such an artificial tendril can change its shape once it is heated in a water bath. So if we look at such a fiber, it just looks transparent. And I would say it looks like a one material type.
Mm-hmm. Now, plant tendrils are quite complicated structures. There's a number of tissues, perhaps 2 or 3 or 4 tissues. How many artificial tissues do you have here?
This is exactly what we learned from you when you explained us the histologic cross-sections of the tendrils. This is a multi-material system that in truth is composed of 2 transparent materials. So here in this specific device, we can unravel the mystery about this as a small muscle fiber, which is relatively stiff and tiny in the center of this tendril, artificial tendril, and it is embedded into a matrix from a super soft material, which is a silicone. And also it looks to the outside as if it would be one material, it is 2. The outside makes it elastic and easily to move, and the small actuator is like a muscle and can move.
So the inner part is relatively stiff and the outer part is relatively
Yes, the inner part
compliant.
is relatively stiff, and that is like an artificial muscle.
Okay.
It contains a microstructure, and the microstructure has 2 components.
Mm-hmm.
One component lets this material move. We call them actuator components. And in principle, this is a crystallization process. And in addition to that, we have a skeleton-forming unit, and this skeleton-forming unit determines the geometry of the direction of the movement, and that is why we can make the system curling. We could also make it bending or stretching, but in this case it is programmed to do curling.
Well, what's really interesting here is that we look at the anatomy of the tendrils. In the biology, there's lots of cells, there's lots of tissue types, there's lots of differentiation, and we ask ourselves, well, how much complexity do we need to make these complicated organizations? You're showing that we can replicate this complex behavior with very, very similar organizations, just with more or less 2 materials. This is amazing.
That is the beauty of this concept, that we do not exactly copy the nature. We extract the principles that are important for one specific function, and we only transfer those components into the synthetic materials that are required. Because the more different components we have, the more complicated is the system.
Some of our tendrils and reactive structures we see in the tropical rainforest, they can be quite big. They could be perhaps 20 centimeters and grab onto trees that are 20, 30 centimeters in diameter. Do you think we'll be able to scale this up to structures which can really exert a lot of force?
Sure. There are different types of upscaling. First of all, we can use the tiny fibers and make bundles of fibers. That has the advantage that we can even imply a superstructure on those single fibers. Or we can just do an upscaling and make something that is small in the same geometry, just larger. That would be a different way of upscaling. But of course, polymers are polymers, and the mechanical strength of a polymer somewhere has some limitations. And if we want to overcome those, we need, again, to make multi-material systems and potentially also to incorporate inorganic compounds.
So also, earlier on, we were talking about secondary growth processes. So we have growth by, we have movement by modification of a material. There's also the idea of growth, of expanding the dimensions for the material.
Sure.
Many of these structures in the biological world, they twine around, but they also thicken. So they tighten onto the support in a second way. Not only do they just roll around, but the diameter of the tendril actually enlarges by normally a growth process. Do you think you'd be able to replicate a second kind of growth process with this kind of structure?
Sure. First of all, one option to get a macroscopic growth is to use materials that are around in the nature and incorporate them. The easiest one would be water, as water transport anyhow is an integral part of plants. We could use swellable components to take up this water and gain volume. So this would be a growth by incorporation of water. Another type of growth is to just create more volume. If we have a compressed shape and we go to a porous shape, we also would gain volume. But it's not the real growth like with plants, because the plants create new biomass. So the real challenge is how to incorporate the white biotechnology so that we are able to convert materials from the environment into new structures.
I see. Okay, so we'll see if this experiment will work now. We have 51 degrees, is that correct? 60?
51, so still maybe on the lower side, but we can try.
Okay, so we'll just put this into the hot water. That straightens out. It's amazing, that was very fast actually.
That was fast, yeah.
Do you measure the reaction time?
Yes, I think here what we need to do is to measure the reaction time depending on the thickness of the coating. Okay. It is clear that we have a thicker coating here, so we have a higher mechanical resistance, we need more actuator phase, and therefore a higher temperature.
Okay, so moving on to the cactus.
Maybe to get an introduction to the cactus, we need to take a look at this scheme, which contains photos that you brought from your visit in Brazil, and also from cross-section of this cactus. And the first initial step that we did when looking at those photos is that we discovered this star-shaped profile. And the star-shaped profile was translated into a computational design for a profile and realized in the 3D printer. And I can show to you how that profile looks like. It is this black elastic material with the star profile here. And now we have those 3 different sides, and those sides can be filled with a material that is able to uptake water. And this very much is inspired by the 3 different cross sections, which are representing the 3 different age levels of the cactus. And we're doing like a time shift by allowing this artificial cactus then to move in between the different time zones. So one looks like a triangle, and if the hydrogel on the outer side is swollen, it is more like a round-like shape.
And will the mechanical properties of this structure change according to these shape
Absolutely,
changes?
Especially if the hydrogel would only be swelling on one side but not the other sides, we would see the material to move. And depending on which side has a swellable hydrogel, we will see movement in the different direction. Also, the bending will become more difficult. So if the hydrogel is swollen on this side but not on that side, bending in that direction will be almost impossible. So we get directional information in the material.
This is very interesting because in the forest in Brazil, the Atlantic forest in Brazil, we see these star-shaped stems that we see in the diagram here, and we see they must have moved. We see that the stem appears to be adaptive to a certain stimulus, and they do appear to move to left or right or to twist around. We don't know the mechanism behind this for the biological material, so it's interesting that our models, our physical models, might give us clues as to how the cactus is actually moving.
Yeah, all would be about water transport. So if we have water evaporation because the sun is shining on one side, it is an open system, it would dry out. If we have rain more coming from one side or faster from one side, we would have this effect. But we learned that the water in this cactus is typically not coming from the outside because it is covered by a skin. And this was the next development step. So we introduced a water channel system into the interior of this cactus. That can be seen here. It allows the water transport to go through the interior of the profile. And then we have those openings here on the side. And this is how the water gets to the hydrogel. So this would be more following the natural system where we have the roots. The roots are transporting the water, and the water leaves on the other side by evaporation.
So at the moment, you're evolving this cactus model step by step, according to observation by observation. And it's a series of fine-tuning steps where we are approaching closer and closer the real structure of the cactus we have.
We are in an intermediate stage between computational design and still iterative classical engineering. Maybe in the future our digital design capabilities will be much better and we can work with digital twins. But in that time we are going stepwise. And the next step already can be seen here. The real cactus has a wooden part in the middle, in the center, and this is already integrated in this version of the cactus.
And this allows a certain mechanical support for the cactus at certain points of development.
Sure, we get the stability, so if the cactus would grow in that direction, the stem would help. And we still have the water transport capability and the ability of the hydrogel to control the movement in the different direction, the searcher capabilities.
What's very interesting here is the tendril movements we're looking at the moment. This is from a tropical rainforest plant where water availability is not a problem. The cactus is a cactus and it lives in an Atlantic forest which has seasonal dryness. So it takes water up, it stores water, and then it uses water in a very smart way within this green hydrogel-like body for its growth and for its movement. So these two systems are very different, actually.
Absolutely, and I think we can explore both options with this setup. And in the future, we might need this cover that is encapsulating the hydrogel so that we have protection to the outside. And we might have a switchable diffusibility of the outer skin so that we can decide if we want to allow the water to evaporate or to be trapped.
Indeed. Our first observations of the cactus shows the skin is about 4 or 5 cells thick. It's about 150 microns thick. And there are what we call stomatal chambers, little pores, which can open and close. And as you just said, they can produce evapotranspiration, which will cause a negative pressure in the xylem wood system, which will pull water through into the system.
This effect might be nicely reproduced by a shape memory polymer membrane because the diffusibility of water in such membranes strongly depends on the temperature levels. It is really the new concept is to take the geometry that is given by the cactus, the water transport system, and to see how we can create new functions from that. It's a geometrical multi-material approach.
And will the outer skin perform a mechanical role? Will it give something for the hydrogel to push against? Can we control the thickness of a stiffer sheath on the outside in addition to the gel?
If we take a shape memory polymer membrane, it will be softer at high temperatures, it will be stiffer at low temperatures, and it's just the question of the thickness of the membrane, how much of an impact this will have on the general mechanical properties of the systems. Yeah, so that is so far the actual status of our work in the GrowBot's project. It just has started roughly a year ago. We'll keep going and we'll keep you informed about our progress.
Right.
Thank you for watching.